Hello, everyone. Welcome to today's live broadcast. Improve your USP LC gradient separation methods following the new 621 guidelines. I'm Bob Aliberta, the Special Projects Director for LCGC, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by Advanced Materials Technology. I would like to share a statement from our sponsor. Advanced Materials Technology is an innovative product development and HPLC column manufacturer focused on improving the presentation of the sample to the detector. From pioneering fused core technology in 2005, the Halo product line has changed previous conventional wisdom that high resolution requires high back pressure. Now, in its 17th year, AMT continues to be a leader in novel, superficially porous particle development, enabling high efficiency and reliability for scientists involved in both small and large molecule separations, and delivers application-specific solutions designed to meet industry challenges. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found at the bottom of the video player. You can enlarge the slide window by clicking on the small icon in the bottom right corner of the media player. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the top right of your presentation window. I would now like to introduce today's speaker. We're pleased to be joined today by Stephanie A. Schuster. Dr. Schuster earned her PhD under the guidance of Professor Joe P. Foley at Drexel University. She joined AMT in June 2009 as a research scientist working with Dr. Jack Kirkland, providing contributions to the commercial development of products designed for peptide and protein separations. Most recently, as part of the technical support team at AMT, Stephanie has been providing customer support in optimizing and troubleshooting their applications. Thank you so much for joining us today, Stephanie, and please take it away.
Thanks so much for the introduction, Bob, and thanks to everybody for joining us today. I'll start with a brief outline of the presentation. So I'd like to first go over the benefits of converting to methods that use superficially porous particle or SPP columns. Then I'll review the guidelines of USP Chapter 621 for changing isocratic and gradient methods. Then we'll look at a few case study examples, including isocratic and gradient methods, and then we'll wrap up with a summary. So let's talk about the benefits of converting to methods that use SPP columns, and really how SPP benefits separations. So I know this slide is really content heavy, so let me step you through it. In the middle, I have an image of a fully porous particle column, and you can see that the pores are really throughout and, through the center and to the edges. And you can compare that to the bottom focused ion beam SEM, where you have that solid silica core surrounded by a porous silica shell. And it's really this particle morphology that enables the high efficiency, high speed separations of superficially porous particles. So in terms of the Van Deemter equation here on the bottom right-hand side, you have H, which is the height equivalent to a theoretical plate, and you have these three A, B, and C terms. It's really the combination of all those three terms being lower or smaller for SPPs that give them a high efficiency. So moving back over to the left-hand side of the slide, you can see we have a plot of plate height in microns versus mobile phase velocity in millimeters per second. We keep the x-axis in millimeters per second in order to kind of be able to visualize it a little easier than linear velocity. So moving from the top where you see that 5 micron FPP in the green or green squares, you can see as you go to the smaller particle sizes, as you would expect, you get lower plate heights. And the lower plate heights are giving that higher efficiency. So as you move from a 5 micron FPP to a 3.5 micron FPP, the curve is getting lower. And then the same thing when you go from the 3.5 to the 1.8 micron FPP in the black triangles. But the take-home message here is that the 2.7 micron fused core particle is the lowest curve on this graph, and that's represented by the orange circles. And you can see we have that 25 to 35% smaller A term, and that's due to the more uniform analyte flow paths through the column bed. For the B term, it's about 25 to 30% smaller, and that's due to the presence of the solid core inside the particles. And then for the C term, that's nice and flat, and that's due to those shorter diffusion distances in the particle. And what I mean by that is that that thin porous shell that we have around that solid silica core. So combining all these three terms is really what enables the superficially porous particles to be run at higher flow rates without compromising the efficiency. So we have an example of that. Here we're showing increased speed and reduced mobile phase consumption. The top chromatogram here is looking at a 5 micron FPP column in 4.6 by 250 millimeter dimension, and that was run at 1.5 milliliters per minute using a gradient of 30 to 60% B in 15 minutes. And this is for a mix of different acids. What we did was we transferred the method to a halo RP-amide column in 2 micron particle size and a dimension of 2.1 by 100 millimeters at a flow rate of 0.5 mil per minute. And we used the same gradient, 30 to 60% B, but now over a shorter time, 3.75 minutes. So this SPP method is 4 times faster than what we had on the fully porous particle column, and it's using 12 times less solvent. But in order to see these really high efficient results, you do need to keep in mind some tips to be successful with small particle and small ID columns. And I'll talk about that as we get further into the presentation. I also want to show this example of increased efficiency demonstrated using fat-soluble vitamins. So I've switched things up here. The blue trace is the Halo C30, and the bottom trace is a fully porous particle C30 column in 3 micron particle size. So what you can immediately see is sharper peaks and increased resolution with that Halo C30 column. And these are run on the exact same column dimension, 4.6 by 150 millimeter. And we're getting more than double the plates for peak 2, which is vitamin E delta tocopherol. We're also seeing a resolution of 1.62 for peaks 3 and 4, which are vitamin D2 and vitamin D3. In terms of the resolution on the fully porous particle column, we only saw a resolution of 0.87. So this, just to sort of reiterate what we saw with the Van Diemter results, we're getting those high efficiency results with the superficially porous particle column. So now I'd like to discuss the USP Chapter 621 guidelines for changing isocratic and gradient methods. And I know that the guidance for isocratic methods has been in place since 2014. So we've been waiting a while for gradient methods to be able to be changed similar to the isocratic methods. So these changes officially went into effect for the U.S. Pharmacopoeia as of December 1st, 2022. And I took a little screenshot of the announcement on their website in terms of when the changes were official. In terms of the British Pharmacopoeia, BP, European Pharmacopoeia, EP, and the Japanese Pharmacopoeia, JP, the changes went into effect as of January 2023. So now let's discuss the allowable changes to USP methods. I have the parameter here on the left, isocratic methods in the middle, and then gradient methods on the right-hand side. So in terms of stationary phase, you must keep the same L category, and that means you can't change from, say, C18 stationary phase to phenylhexyl stationary phase without doing a revalidation. So you just have to keep that same L category, and all of those L categories are listed on the USP site. You are able to change from a totally porous particle, TPP. I refer to them as fully porous particles, so these two can be used interchangeably to SPP columns. That is allowed. So that's been in effect for isocratic methods, and now that's available also for gradient methods. In terms of the column dimensions, the particle size and/or length of the column may be modified, provided that the ratio of the column length, L, to the particle size, dP, remains constant, or in the range between -25 to +50% of the prescribed L to dP ratio. So I have a little asterisk here. They do offer some guidance on changing from TPP to SPP columns, and that is you can use other combinations of L and dP, provided that the plates are within -25 to +50% relative to the prescribed column. And I have an example of that as we go along in the presentation. The same thing applies for column dimensions for gradient methods, but I have a little caret here, and that means in terms of other combinations of L and dP, instead of plates, you're able to use the ratio of the retention time to the peak width squared, which would essentially give similar to plates, but we can't measure plates under gradient conditions. But that would need to be within -25 to +50% relative to the prescribed column. And they do also specify that the changes are acceptable provided that system suitability criteria are fulfilled and selectivity and elution order of the specified impurities that are being controlled are demonstrated to be equivalent. In terms of the internal diameter, the change is allowed for both isocratic and gradient methods. And for flow rate, you would need to scale it according to this equation here, where F2 is the new flow rate, F1 is the original flow rate, and that's multiplied by the column diameter, the new column diameter squared, multiplied by the original particle size, divided by the original column diameter, and that's multiplied by the new particle size. So continuing on with the allowable changes, there is no change allowed to detector wavelength for both isocratic and gradient methods. In terms of the mobile phase composition, for isocratic methods, the amount of the minor components of the mobile phase can be adjusted by plus or minus 30% relative. However, the change in any component cannot exceed plus or minus 10% absolute. And then in terms of gradient methods, the gradient time may be adjusted by this particular equation, where Tg2 is the new gradient time, and then that's calculated by using the original gradient time multiplied by the original flow rate divided by the new flow rate, and then the new length and the new column diameter divided by the original length and the original column diameter. In terms of pH, that can be changed plus or minus 0.2 pH units for both isocratic and gradient methods. The buffer can be changed by plus or minus 10% for both isocratic and gradient methods. And then the injection volume can be scaled according to this equation here. And that's applies for both isocratic and gradient methods. The column temperature can be changed by plus or minus 10 degrees for isocratic methods, but only plus or minus 5 degrees for gradient methods. So I know this is a lot to absorb. One thing that makes it a little bit easier is to use a method translator, and I've listed 2 different ones that are available. The first one is from the University of Geneva, and that's available as a downloadable Excel spreadsheet. And I have the web address here. And then the second one is from ACD Labs. They have a method translator freely available on their website. One thing that is nice about the one from ACD Labs is that it also lists typical dwell volumes for different HPLCs and UHPLCs. I do have some words of caution for moving to smaller particle sizes and smaller column IDs. So those smaller particle sizes and smaller column IDs are more susceptible to extra column band broadening. So extra column band broadening also is known as dispersion. And in this diagram of an HPLC system, everything inside the dashed black line represents sources of extra column band broadening, in particular the pre-column and the post-column. And then, of course, there would be dispersion from your analytical column as well. So this is just the total band broadening. But anything outside of the column would be the extra column band broadening. And in yellow, I have the pre-column dispersion, which includes the sample injector, the injection volume, and the pre-column tubing. And then in red highlighted, we have the post-column dispersion, which is impacted by the post-column tubing and the flow cell or ionization source. So these are the 2 areas that you would need to worry about or improve in terms of getting the most performance out of those smaller particle columns or smaller particle size columns and smaller ID columns. In terms of if you're running isocratic methods, it's really the pre-column dispersion that has the most impact. And if you're running a gradient method, it's really the post-column dispersion that has the most impact. So what are the ways to reduce that extra column band broadening or dispersion? One of the easiest ways is to use the shortest and smallest ID connecting tubing between instrument components. So I have a picture here of a Marvel Exact connector. These are finger-tight zero dead volume connectors that we recommend. I know there are other sources of zero dead volume connectors. Part of the reason that we like these is that for the design of these connectors, when you tighten them down, it's not possible to over-tighten them because after they're fully tightened, you both hear and feel click. So I think that's a nice part of the design of these connectors. The next way to reduce extra column band broadening is to use a smaller volume detector flow cell. So we recommend 2.5 microliters or smaller. The other way is to increase the data acquisition rate. So since you have these really small peak volumes, you don't want to undersample them. So we recommend using 20 hertz or higher for the data acquisition rate. And then finally, you are able to decrease the injection volume. And this is actually more critical for isocratic than gradient separations, because with gradient separations, as I mentioned earlier, it's really the post column impact that really would make the gradient separations not look as good. But with in terms of gradient separations, you usually get some focusing at the head of the column because you're injecting out of a lower mobile phase solvent strength. So that's actually usually to your advantage, and you're able to inject more. So here's an example of extra column band broadening impact on both resolution and efficiency. This is an isocratic separation using a Halo 90 angstrom C18 column with 2 micron particle size and 3 by 150 millimeter dimension. The extra column volume is 64 microliters, and we used a flow cell of 12 microliters. You can see this area that's highlighted red. We're not really getting baseline resolution of this cluster of 3 peaks, and our plates for the last peak are 18,300. So by reducing the excess volume in the system, so we've reduced it to 16 microliters of extra column volume, and we used a flow cell of 1 microliter, we're able to see an average of 50% increase of plates just by reducing that extra volume in the system. And this, you can see the area highlighted in blue, we're getting baseline resolution of those 3 peaks that weren't baseline resolved in the top chromatogram. So now let's review some isocratic case studies. And I know this is another content-heavy slide, so bear with me as I step you through it. In terms of what changes are possible, so the top chromatogram in black used a 5 micron fully porous particle C18 column with 4.6 by 150 millimeter dimension. And we've calculated the L to DP ratio to be 30,000. So for minus 25 to 50%, our L to DP can be in the range of 22,500 to 45,000. The data, stepping down to the data in green, we use the same particle size, 5 micron, but now using a superficially porous particle column and in 4.6 by 150 millimeter dimension. So technically, the L to DP ratio is still 30,000, which means the criteria is met. And just by changing from a fully porous particle column to a superficially porous particle column, we're seeing an increase of 37% higher plates and a resolution going from 1.34 to now 2.53. If we want to improve it even further, we can go to a smaller particle size, superficially porous particle column with 2.7 micron particle size and now 4.6 by 100 millimeter dimension. In terms of the L to DP ratio, we're looking at 37,037. So that means we're right in the middle of this criteria, and we're getting 57% higher plates and even better resolution at 3.29. And then finally, if we really want to increase the speed and throughput of the method, we can move to a 2 micron superficially porous particle column in 2.1 by 50 millimeter. And now we're still meeting the criteria with an L to DP of 25,000, but our runtime is 3 times faster, and we're looking at 41% higher plates. So you can see And our resolution is 2.31, and we've expanded that here so you can see that indeed those peaks 2 and 3 are baseline resolved. So these are just some of the examples of what you can do if you are starting out from a 5 micron 4.6 by 150 fully porous particle column. Going back to increased speed without loss of resolution, on the top here we're running a 4.6 by 250 millimeter 5 micron column in fully porous particle morphology at 1 mil per minute, and the total runtime is 12 minutes. So in this case, we have the HPLC in what we call the standard configuration with an extra column volume of approximately 35 microliters. It's using a standard flow cell of 14 microliters with a 0.5 second response time, and it's using the standard length and ID tubing. So if we optimize this for a halo column, what we've done is we've shortened the column to 100 millimeter. We're using a smaller particle size, 2.7 micron, and we've increased the flow rate to 2 mils per minute. So in order to see these results, we had to reduce the extra column volume to 10 microliters. We used a 5 microliter semi-micro flow cell with a half-second response time, and we've reduced the length and ID of the tubing. So in terms of the overall runtime, it's now 6 times faster. So we're seeing a 2-minute runtime with similar plates. If you calculate the L to DP ratio, it's slightly below where it could be with 37,000. Technically, it needed to be 37,500. But we are meeting the criteria for plates because that could be anywhere from 19,425 to 38,850. And you can see our plates were 24,500. So in terms of meeting the criteria, this example would meet it. Here's the USP monograph for estradiol in modified condition. So in this case, we used a 1.5 by 100 millimeter column, Halo C18 and 2.7 micron particle size. And in terms of the L to DP ratio, it could be anywhere from 22,500 to 45,000. And we're looking at 37,037, which, is in the middle of that range for L to DP. The original method used a 3.9 by 300 millimeter column, and I did notice a typo here. This 3.9 by 300 millimeter column was a 10 micron particle size, so I have an extra 0 before the 1, which that should be 0.01 instead of 0.001. But running that particular column at 1 mil a minute for a total of 8 minutes gives 8 milliliters in terms of volume used per run. Using the modified method of a 1.5 by 100 millimeter column with a flow rate of 0.2 milliliters per minute and a total runtime of 1.5 minutes, that gives a volume of only 0.3 milliliters. So that represents a 96% solvent savings by moving to that smaller ID, shorter length, smaller particle column. So now let's examine some gradient case studies. But before we do that, I do want to point out when you're making these changes, you do have to take notice. And this is specifically called out in the Chapter 621 guidelines. So in terms of the adjustment of conditions with gradient elution for HPLC, this is more critical than with isocratic elution, since it may shift some peaks to a different step of the gradient, potentially causing partial or complete coelution of adjacent peaks or peak inversion, and thus leading to the incorrect assignment of peaks, and to the masking of peaks or a shift such that elution occurs beyond the prescribed elution time. So really what they're saying is just be aware that when you're making these changes to gradient methods, you could potentially change the elution order of the peaks. So you just have to be aware of that and make sure it doesn't happen. For some parameters, the adjustments are explicitly defined in the monograph to ensure the system's suitability. So in terms of dwell volumes, not all of the monographs list the dwell volumes. So that's one thing that you do also need to be aware of. So now let's take a look at the USP monograph for cobamamide. And this is the original monograph with the monograph column results here in black on the top and the halo results on the bottom in blue. Cobamamide, which is the peak labeled 1, is also known as adenosylcobalamin, and that's one of the biologically active forms of vitamin B12. In terms of the L to DP ratio, that could be anywhere from 28,846 to 57,693. And you can see for the L to DP ratio of the halo column, we're right there in at 37,037 for our 4.6 by 100 millimeter column. In this particular example, all we did was use the same conditions as stated by the monograph. We just had that small particle size change from 2.6 to 2.7. For the suitability requirements, the column efficiency has to be no less than 22,000 plates, and the tailing factor has to be no more than 2. So for the monograph column, it was able to pass both of those system suitability requirements, and the halo column passed those system suitability requirements as well. There is a system suitability mix for this particular method, and you can see that the elution order is identical on both columns. So we're seeing a slightly higher back pressure on the 2.6 micron SPP column, as you would expect. It's about 506 bar compared to 490 bar on the 2.7 Halo C18 column. So this meets the system suitability, and there are relative retention times. And in terms of relative retention times, the USP doesn't have any pass or fail criteria for that. So then we wanted to modify the original method to both speed it up and use less solvent. So what we decided to do is run on a 2 micron, 1 by 75 dimension column, and we use this equation here in order to calculate the new TG, the new gradient times essentially. The flow rate was also increased to 0.4 milliliters per minute instead of 0.25 milliliters per minute, which would have been the same linear velocity as the 1.2 milliliter per minute flow rate of the original monograph. We also increased the equilibration time by 4 minutes for 20 column volumes, and that gave us a total runtime of 25.5 minutes. And I've plotted the gradient program here. You can see that it's a really complex segmented gradient. And the good part about it is that we really don't have any critical pairs in terms of those 4 system suitability peaks that I showed on the previous slide. We also reduced the injection volume to 0.8 microliters from 5 microliters using this equation here that I had shown previously. So I have the original monograph results here with a 45-minute runtime at the top, and then with our L to DP ratio of 37,500, you can see we're now almost running 2 times faster with our modified method, and we're only using 10 milliliters per run of solvent compared to 54 milliliters per run, which is a 5.4 times less solvent used using the new method. And in terms of using the smaller particle size, smaller ID, shorter length column, we're seeing a back pressure of 540 bar compared to 506 bar on the larger particle, larger ID, and larger length column. And then just to emphasize, the elution order using that system suitability mix is identical on both columns. We're just we're able to speed things up by using that faster flow rate, smaller particle size, smaller ID, and shorter length column. So you get both that solvent savings and speed savings. And then in terms of that 2.6 micron SPP particle size compared to our Halo 2.7 micron particle size, there really is no significant difference in the particle size other than some slightly better standard deviation for the Halo column. So, you can see the standard deviation reported here was 0.013 compared to 0.024 for the 2.6 micron SPP column. And now here's another example using the USP monograph for itraconazole. Itraconazole is an antifungal medication, and it's used to treat different types of fungal infections. So in terms of the L to DP ratio, this original monograph column is 3 micron fully porous particle C18 in 4.6 by 100 millimeter dimension. And I can see my hyphen for the gradient turned into a funny symbol here, but that should be 20 to 50% B in 12 minutes. You can see, again, we're meeting that L to DP ratio range since we're at 37,037. All we did here was swap out the same column dimension, the 4.6 by 100, but using the Halo 2.7 micron particles. For the system suitability, the tailing factor has to be no more than 2, and the RSD has to be no more than 2%. So the original monograph column was able to pass those criteria, as was the Halo C18 column. So in terms of speeding up the method was moved to a shorter SPP column with both smaller ID and smaller particle size. In this case, we moved to a 2 micron Halo C18 in 2.1 by 50 millimeter dimension. We reduced the injection volume to 1 microliter, and we've scaled now the gradient to 6.26 minutes for the overall runtime. And you can see we're just at the 25,000 L to DP ratio cutoff, which meets the criteria for the original column. And our total runtime now is greater than 3 times faster with the Halo column. And then finally, in terms of the mobile phase reduction, for 10 injections using the original monograph conditions, you'd be using 300 milliliters of mobile phase. And that's compared to only 30 milliliters of solvent switching to the 2 micron Halo column, which represents a 10 times reduction in mobile phase used. So for labs that are looking at reducing their chemical footprint and maybe also want to reduce their waste disposal cost, moving to the smaller particle, smaller ID, and shorter length columns would really add up to big savings over time. So then in terms of a summary, hope I've convinced you that halo columns are made for ruggedness with high efficiency and high-speed separations. It is important to optimize the instruments in order to gain the most benefit from halo column technology. And then finally, following the new USP guidelines for gradient method modernization enables both FPP and SPP methods to be improved for speed and mobile phase savings using Halo fused core column technology. Then I do have a few acknowledgments. I'd like to thank the team at Advanced Materials Technology, specifically Peter Pellegrinelli, Connor McHale, Dr. Taylor Harmon, Ben Liebert, William Miles, Dr. Chuping Liu, Dan Messick, Melissa Ash, and Stephanie Rosenberg. And I'd like to thank you for your attention. And if you have any questions, I'd be happy to answer them. And now I'll turn it back to you, Bob.
All right, fantastic. Thank you for that informative presentation, Stephanie. Before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found directly below the video player. So our first question of the day is, if we meet the L to DP and or number of plates criteria, do we still need to fully revalidate the LC method?
Oh, that's a great question. So you don't have to fully revalidate. What you would have to do is a verification. And verifications are described in Chapter 1226 of the USP. And in there, it basically says you can do some of the things that would be done for validation, but you don't have to go through a full revalidation.
All right, great. And I'll throw the next question at you from the audience. The audience asks, what is the part number and make of the tubing that doesn't over-tighten?
Oh, so that's the Marvel Exact tubing, and it's available on the halocolumns.com website. It depending on what ID and length you need, that would determine the part number. But if you go to our website, the Marvel Exact tubing is listed there, and if there are lengths and IDs that you'd rather have, those are available from the IDEX website.
Awesome. Thank you for that info there. Here's the next question. This question refers to your slide, FPP to RP Halo. Do you change the acquisition rate? The audience asks.
Oh, sure. So for our methods, we usually just keep the acquisition rate at the highest level because it doesn't really hurt to have it so high as long as you don't get too much noise in your baseline. So in that particular example, we used the same data acquisition rate, which was probably 100 hertz or better.
Excellent. And what LC and detector were used for this work?
Oh, very good. So we're mainly using the Shimadzu Nexera X2, and the detector is their M30, which is a photodiode array, which has a 1 microliter flow cell.
Great. Okay. Here's your next question. When you say your gradient was 30 to 60% B, are you holding the gradient at any point or simply setting starting flow at 30% B and set to 60% B at 3.75 minutes?
Oh, I think in that case, we didn't have any isocratic hold at the beginning. We just went from 30 to 60 over the specified time.
Quick and easy answer. Great. So why would someone want to use USP methods?
Oh, sure. So the USP methods have already been validated. So this really saves a lot of time for labs that are making generic versions of the pharmaceuticals. So it really helps you not have to start out your method development from scratch. So that's the advantage of using the USP methods.
Fantastic. Here's the next question from the audience for you. What pore size is recommended for peptide analysis?
Oh, for peptides, we have a particular 160 angstrom pore size for peptides. It really depends on what size peptides you're talking about. So if they're not too large, you could use our 90 angstrom pore size. But if you have like a bigger range of peptides, say up to maybe like 10 or 15,000 molecular weight, I'd recommend the 160 angstrom pore size.
Great. So here you go. How does one obtain an official system suitability mix?
So those are available from the USP website. So if you just go, there's a USP store, and you're able to buy the system suitability mixes there. Also, they are resold by Sigma, so you can get them from Sigma Aldrich.
Fantastic. Thank you for that info there. So the audience is asking, are halo columns stable at pH 10?
Oh, pH 10 is not recommended, unfortunately. So we at this point, we don't have any phases that we'd recommend to pH 10.
All right. And let's see here. Our next question is, how does the data acquisition rate impact the chromatography/peak shape?
Oh, sure. So I probably should have included an example of this, but what happens is if the data acquisition rate is too low, then the peaks will appear broad and the plates will be low. If you have it too high, then your baseline will appear noisy. So the key is to really set it to at least 20, because we want to get at least 20 to 30 points across the peak. And if the peaks are coming out fast and if they're narrow, that's why you need to have the data acquisition rate set higher.
Excellent. Thank you. Just a quick announcement for the audience. We did receive a question that asks, what about the back pressure on this one? I feel like we might need a little bit more follow-up, a little bit more clarity on that question. If you'd like to submit another question that gives a little bit more info about what you're asking about, feel free to throw it into the Q&A box and we'll follow up at that time. So next question for you, Stephanie. I have method, pardon me, what constitutes a revalidation versus a verification?
Okay, so a revalidation would need to be done if you made a significant unallowed change to the analytical method, such as changing the chemistry of the stationary phase from, say, like C18 to phenylhexyl. A verification is done when the analytical method has been changed according to the guidelines, such as a change from a fully porous particle to a superficially porous particle column. So a verification is less involved than a complete revalidation.
Great, excellent info there. So here's your next question. I have methods with 2.6 micrometer and 1.7 micrometer particle sizes. So I can move these methods to 2.7 micrometer and 2 micrometer particle sizes without revalidation?
That's right, but you do have to make sure that you meet the system suitability, and then you could also do the verification of the method, as we just described.
Perfect, thanks. If I move a method which uses fully porous packings to superficially porous packings, can I just change the column or do adjustments need to be made?
So in that case, I would recommend, sometimes you can use faster flow rates with superficially porous particle columns. So that would, I mean, you could run it just as written, but if you really want to get the true benefit of that superficially porous particle column, then I would recommend increasing the flow rate and then also doing the verification and making sure the system's suitability is met. We also have a method conversion guidebook on our website at halocolumns.com that goes through the steps of switching a method from an FPP to an SPP column. You just need to search method conversion guidebook.
Fantastic. The audience asks, what is the pH range for a halo column and where can I buy it?
Oh, sure. So the pH range really depends on the stationary phase. For the examples that I showed today, for the Halo C18, those are rated from pH 2 to pH 9, and you can buy them from several different sources. If you go to if you're a US customer, you have multiple different options. You can buy them direct from our website, you can buy them from MacMod Analytical, or you can buy them from VWR.
Well, thanks for that info there. So are there any issues with upgrading to a UHPLC system and still being in compliance with these modernization allowances?
I'd say there's really no issues. You just have to make sure that you're meeting that system suitability criteria, and and it's actually maybe a little bit easier if you're using a UHPLC, because in general those systems are already optimized for low extra column dispersion. So that would really be to your advantage to use one of those systems.
Great. Here's your next question. Why should the temperature change allowed be different for isocratic and gradient separations?
I think so. We'd probably have to go direct to USP for this one, but I think they sort of erred on the side of caution, and they didn't want to change it too much, just in case there could potentially be elution order switches or peaks co-eluding, perhaps. I think that's why they went on kind of the more conservative side for temperature changes.
Fantastic. Here's your next question. Is there any chance of having peak tailing after long HPLC runs?
I'd say it really depends on the method conditions that you're using and perhaps even the age of the column. So, and maybe also the identity of the compound that's tailing. So I would probably look at some kind of like before you started the analysis versus after you started the analysis, in terms of how much tailing has increased, for instance. But I think, that it is possible for the tailing to increase. Just really depends on a bunch of different factors.
Very true. Very true. So what kind of halo column is suitable for peptides analysis by LCMS?
Oh, that's really a great question. So we offer 3 different stationary phases for peptide analysis. We have a ESC18, a phenylhexyl, and also ES cyano phase. I think for LCMS, any one of those 3 would be fine. Typically, people go for the ESC18 because that seems to be, a catch-all for the broadest range of peptides that you might see.
Great. And does Halo make monolithic columns? Are monolithic columns USP approved?
Halo does not make any monolithic columns, but that's a really great question. I think there haven't really looked for any monolithic columns in any of the monographs, but I don't see why they wouldn't be approved. So I think that would also be an option to move to.
Excellent. And here's the next question from your audience. They asked, when performing method verification, what are the critical parameters to be verified, such as precision, specificity, etc.?
I think it really depends on what particular method you're going for, whether it's assay or impurities analysis. So I think it really is kind of dictated by the method itself. I wouldn't really I don't think I can really answer that without knowing a specific monograph method.
All right, excellent. And since we do have a few extra minutes still left on the clock and we're running low on questions, we will give a few moments here to see if any follow-up questions or any more questions come in. Remember, you can type your questions in the Q&A box below the video player. So we'll hold for a few minutes, see if any more questions come in. And thank you for hosting this Q&A session, Stephanie. And I'll throw the next one at you as soon as it comes in.
Okay, fantastic. And also, if anyone is interested in the slides, we can make those available. We're, really more than happy to help people with their methods, and this is really part of our goal as a company. So we, in terms of troubleshooting and helping improve methods, that's really our goal.
All right, looks like we've received a question here for you. C30 gives too many peaks for peptide. Why is that?
I'm not really sure of the too many, what's meant by too many peaks. Maybe if you want to contact, or I could reach out to you after the webinar, you could show me the chromatogram and we could take it offline and discuss it.
All right, great. Thank you so much, Stephanie. With that, we will wrap up. I want to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, Advanced Materials Technology, for making today's webcast possible. We would like to ask everyone in the audience to participate in a brief survey. This survey will appear on your screen after today's presentation has ended. You will receive an email alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. We hope to see you all next time, and goodbye.